So I have made you a co-host, so you should be able to share. I've already started the live stream and also as a backup. So you can share your screen and proceed. So before you do that, just I wanted to make two announcements. Okay, for next semester, see, usually I offer model checking and this SMT course with different applications alternately in the two semesters that I teach. So it's just a plugin for the course that I'll be offering next semester to encourage you to take it. So this time, next semester, I'm doing something slightly different. Of course, model checking I have to offer so we've discussed, and then there is usually the model checking course is what is called a core elective, which means people wanting to specialize in verification area. For them, this is like one of the core electives that they'll have to take. This as you can take model checking. So this is a model checking course, but with more emphasis on software. So I've decided the traditional model checking course takes a slightly different thing. It is application agnostic. Okay. So, it covers a lot, both symbolic model checking as well as Buki automaton kind of thing, but it is application agnostics in the sense it can be used both for software in general computational system or models of computational system described at a high level. So this time, the next time in January, what I'm doing is I'm covering some basics of model checking, but couched inside software analysis. So the emphasis will be on analysis of software. Okay, software analysis, which means both verification analysis. Model checking is one of the methods, and I'll be covering this course. I plan to cover another very popular software analysis for verification, which is called static analysis or abstract interpretation, and some basics of programming logic, which you saw a little bit of in this course as well, a little bit more of that. Program logic, and then I'll be covering model checking as well as abstract interpretation, which abstract interpretation is something that is specifically tailored for software verification, and a little bit of software program synthesis as well, application of these logic techniques for synthesis. So the course is titled software analysis and verification. Okay, so the USP is both model checking and abstract interpretation will be covered from with emphasis on software analysis, how you model software programs, code, at that level. So it should be interesting, and I encourage you to take it. Yeah. Okay. Go ahead, Devji.
Okay, sir. I'll start by sharing my screen, I guess. Just a sec. So it's visible, right?
Yeah, it is. Yeah. Now it is. Yes.
Yeah. So I'll be comparing DPLLT and Reluplex on verifying DNN, and I'll show how Reluplex can perform better than DPLLT. Okay. So our problem here, we'll take a very simple problem here for seeing the properties of DPLLT and Reluplex on a very simple neural network, which will have one hidden layer and one input layer and one output layer. So, and these are the weights of the DNN, which we have seen a lot of times. So now let's encode this DNN into a formula which can be pushed into a solver like a DPA, which uses DPLLT or into Reluplex. So first of all, we have this condition. So here, the property which we will be looking at is that if there is an input which is greater than 0, if it can give us an output which is in between 0.5 to 1. Okay, so that is the property which we will be checking. So this is the input property which is said to be hold. Again, we say that v1 is again less than 1. So v1 is in between range of 0 and 1. Then if there is a input which will give us a value of v31 in between range of half and 1. Okay, now here we encode the ReLU neurons, which is v21 and v22, like this, likewise like this. So these are all the clauses which will be sent
Wait a
into
minute. So Debjit, so
Yeah.
there is a mistake, I think. You said v31, you expect it to be between 0.5 and 1, correct?
Oh, yes. It is less than
or equal to 1. Okay.
Yeah, it's less than, yes. So otherwise we encode the network this way. That is like v11 greater than 0. It means that v21 it must be equal to v11. And v11 less than 0. It means that v21 should be 0. And likewise. So this encodes the whole neural network, and it will also check the property if this holds or not. And we can also say that, so we can just use a Z3 solver to solve this. Now, again, I will explain how the DPLLT solver solves this. So here we'll be using so first of all, I changed the implied formula into an AND formula. I think these should be ORs. Okay. There's another.
This is CNF. Yes, that should be.
These should be ORs. Okay. Now, so here I'll be using online DPLLT. Now, online DPLLT is very similar to DPLLT, except we just do an eager T reduce and we just analyze a conflict as soon as it comes along. So here in DPLLT, we usually assign propositions to each of these clauses. So each of these unit atoms in some sense. So these are all unit atoms, and we assign propositional values to these unit atoms. And then we try to see that if any propositional assignment of these unit atoms holds, plus with having solutions to the propositional atoms in the T solver. It means that like here you have a OR, right? So if you have a OR here, it should be this or this. So we have choices here. So if we pick one of these choices, we can see that like sometimes the DPLLT will solve it, otherwise it won't. I'll give you more examples as we go along. I'll also explain what T decide is, what T deduce is, what T analyze conflict, and T backtrack is using an example. So yeah, so here we have encoded all these things into a propositional atom, which is B1, B2. So this gives rise to not of B1 or B3, and this gives rise to B1 or B4, and this gives rise to B1 or B5, and this gives rise to not of B1 or B6, and we encode this as B7, and again B8, B9. Okay, so just ignore this. I had drawn a picture of this. So here, first what we do is that we do T decide. Okay, we decide which atoms should be one. So we start with the one which is like has the lowest lexicographical order. Okay, so we say that B1 is true. Okay, this will be our first step. Okay, next we say that
that is the order, Debjit, that is the variable decision order that you have chosen, correct?
Yeah, like,
for illustration.
yeah,
But it
exactly.
should work for anything, any other order as well.
Any other order, it will change. So I had, so if I suppose say that like I change this ordering of things, that is like, suppose
So I just to be clear, okay, I mean for myself, so you are going to be deciding on the variables in what you called as lexicographic, which is actually in the increasing order of their index. Is that right?
Yes.
Okay.
So here I have said that here we have B1 and it's in the level of 1. Okay. So this is true B1 in level of 1 is what I have decided, what has decided. Now again, B2 at a level of 2 is again 1. Okay. B2 at the level of 2 is true. Okay, this is what I have decided. Now we will use T deduce because this is DPLLT online. So this does a T reduce operation, and we see that B3 also have to be true. It comes from the clause 3. Okay, because if this is true, this will be false. So for this clause to be true, this have to be true. Okay, and this is again in the level 2 because this is not an explicit derivation. Okay, now here we can also see that B6 also have to be true. Okay, so we decide, so this is again an implied decision that B6 have to be true. Okay, and these are all at level 2s because these are not like new assignments. These are just implied assignments.
No. Actually, I think your convention is wrong. Okay, so because see, you're still propagating the consequence of a decision at level 1, isn't it? See, you made B1 true at 1. That is the start. So you haven't made the decision at 2 yet.
Okay.
Because okay, so you see, you just plugged in B1. So this would be, as per convention, all be at 1. Okay?
These should be level 1.
1. Okay, because all the implied literals at level 1 will also be labeled.
Yeah, because once you do T decide, it will always T deduce once, and that is when
part of T deduce what is Boolean constraint propagation, BCP, which is also part of T deduce. Of course, T deduce does more. It does theory things as well. We get to that. But all I'm pointing out is they be 1. Okay.
Yeah, these should be 1. Yeah.
Okay.
So these should be 1. Now what we do is that we assign more variables like B4, B5, B7, and B8. All of these to be true. Okay, because we are going in a lesson.
Go one step at a time. So
so B4.
So you did okay. So you got B3 and B3 and what is this?
B4.
No. B4. Okay, so that you got by because C4 became unit. So those two got reduced. Okay, similarly, okay, you're still doing Boolean constraint propagation, T deduce, correct? So there are more things.
No. So you cannot do BCP here. Okay, because
why? Listen to me. Because you made a decision of B1. Okay. So this C5 goes away.
Yeah.
Okay. C4 and C5 go away because they reduce to true, correct?
Yeah,
that is good. Yeah. So this is B6, not 4. The one this one. That is B6 as a result of 6, correct?
Yeah, this is B6.
Okay. Got it. So then it settles. Therefore, now you have to make further decisions, correct?
Yeah, it's T decide now.
Yeah, okay. So, but I thought you chose to decide on B3. What is it? You've written it
B3
so.
is already decided here.
Yeah, but what is this at the top, at the level of
This,
2?
right?
B2,
This.
B2, that's B2. The one left to that.
This is B2.
Yeah, but is that the explicit decision you made at level 2?
Yes, we have to make this explicit decision. That is
Okay.
B2 is true.
Yeah, okay. So start with that, okay?
Yeah.
When you do that, what happens? Explain, okay? What happens?
Oh, okay. So when I do that, nothing changes. And this have to be true anyway, because this is clause.
Correct.
Okay. So B2 has to be true.
And there's no implied literal as a result.
There is no implied literal.
Okay, go ahead. Okay. Yeah.
Okay. So now I do T decide on B4. Okay, because B3 is already done. So lexicographically, B4 comes next. So B4 is again decided, T decided. Okay, now nothing is implied here. Okay. Now again, B5 is T decided. Well, you can see nothing is implied here. Okay. So again, B7 is decided, whereas nothing is implied here. Again, B8 is decided, nothing is implied here. But we can see that like once we do T deduce, we will see there is a conflicting clause. Okay. Now I'll show you what the conflicting clause.
Which one? Just see. So which clause is giving rise to the conflict? Okay. Which one? Can you tell me which one?
So clause? Yeah, so this is the cut which will give rise to the.
I understand. First, tell me which clause.
Oh,
you plugged in all these things in some clause to get the conflict. I want to know which clause is that in your thing. Is it no. Yeah, is it C7, C8? Name the clause that resulted in the conflict.
No, so I mean there is like no clause. I can actually make a conflict. I mean, it's a conflicting clause, right? I have to make a conflict.
No. This K is a conflicting node, correct? So why was there a conflict? When you plug in all these things into what? Okay. Why did this? So the 1, 2, 3, 4. There are 4 arrows coming in. Yeah. Resulting in a conflict.
Yeah.
When does a conflict happen? When some clause reduces to, simplifies to false.
That is just, so that happens in CDCL, but like I think T deduce does something more. No. It gives us a bunch of clauses.
No, I'm asking you, why is there a conflict? Simple.
Okay.
Why is there a conflict? I mean, I know that these decisions were all implied, okay, or explicitly made, okay? Yeah. And you said there is a conflict.
Yeah.
I don't know why there is a conflict. Explain why there is a conflict.
Yeah. So here you can see that like B8 should be less than, should be greater than V31. Okay. Whereas V31 is equal to V21 plus V22. Okay. And now if I choose V4 to be true, it means V21 is 0. It means this is 0. Okay. And V22 is 0 means that this is 0. Okay. Now V21 and V22 both are 0. It means V31 is 0. So here is the conflict.
Okay. So this is really a theory conflict. Okay.
Yeah, this is
the reason for the confusion was, see, there are 2 kinds of conflicts. One strictly at a Boolean level. Okay. That can happen too. Okay. And now what you're illustrating is T-reduce kind of checks both. Okay. They can be just Boolean conflicts. Okay.
Yeah.
Now there was no Boolean conflicts here, but then you sent these decisions to the theory solver, and then you notice a theory conflict. Okay.
Yes.
Yeah. Okay. Good.
Yeah. There also can be theory plus a Boolean conflict. That will T-deduce will also detect that. So here, we add a conflicting clause to our whole set of literals. Okay. Now we do the same thing again here also. Okay. So first of all, IT decide B1 to be 1. Okay. Now it will show me that like B3 is here. There is a mistake again. This level should be 1. Okay. So B3 is again implied to be true. And again, B6 is implied to be true. So these were again, whatever there was, we would just essentially backtrack to this level. Right. So we would backtrack to this level and only these 4 nodes will remain. Okay. And once we have backtracked.
Which 4 nodes?
Only these 4 nodes.
Okay.
Wait, why will it be these 4? Shouldn't it just be the 3, B1, B3, and B6? Or
B1, B3, and B6. Oh, if you are getting to the next, so I mean, it should. Wait, is this making it a unit literal? Just let me check once. No, I think no, B2 can be here, right? Because so first of all, we would want CC1 to be unit literal when it goes away, right? When we cut the conflicting clause, right? Yeah. But here, so here, if so, but now if we just, so B2 is not here at all. So I don't know why it would matter if we go back 1 level up.
See, when you backtrack, so when you backtrack to the level other than the latest level at which the conflict occurred. Okay.
Yeah.
You know, the earliest level other than the level before the conflict occurred. So which in this case, it would be B1, level 1, correct?
Yeah. Oh, okay.
Oh, no. It is, okay, all these things are at 3. No. All, okay, so there were lots of decisions made, 5, 6, and so on.
Yeah.
So you are, the earliest level other than the thing is 2, correct?
Yeah.
Correct.
So
you backtrack to 2, correct?
Yeah, exactly.
Yeah. So I think it's correct, right? Yeah. So
yeah, I got it.
Yeah, the earliest.
I also think
it's correct. Yes.
Yeah. So we backtrack it to level 2. Now again, we would use this, and we would say that like, so here we can also say that like D6.
So no. First, go step at a time. So when you backtrack, you keep backtrack to level 2. So which means you have kept all these decisions. Okay.
Yeah.
These 4 decisions.
Yes.
So this becomes a unit clause immediately. Correct.
Yeah.
The CC1 becomes because you have B4, B6, B7.
Yes. No, I don't have B6.
It should be B4, B5, B7, B8, right?
Yeah, I think so. Something
B4, B5. Just a sec. Let me check once.
Yeah,
No. It should be this. This is the picture actually for that. Just a sec. Let me check. No, it is fine actually. I just made a mistake while planning the slides. So CC1 should come here basically. So this is the picture. So B6, B4, B7, B8. Okay. B6, B4, B7, B8. Okay. Now I add this as a conflicting clause. Okay. Now I make the decision that it will be not of B4.
No. You first backtrack. Okay.
Yeah, I first backtrack.
At that point, when you backtrack, you I presume you will. Okay. Because usually what happens is that if you backtrack, the conflict clause that you introduced, it flips one of the earlier decision. Okay. As a result of Boolean constraint propagation. So in this case, what are the things? So what was B4? It was B4 was true. Okay.
Yeah.
So this becomes 0. Okay. What was B6?
B6 was true.
Where?
B6 was true here.
No, so B4 was at a later level, right? So at level 2, we are only having B6, right? So right now.
Yeah. So so at level 2 we only have B6. Yeah. So here in this case we don't have a unique
See, this is
identification
actually
point.
not a well. Yeah, this is. I'm not sure if this is. Yeah. So what? Yeah. Go ahead, Diganta. What did you? What was your question? Yeah.
No, I'm just saying that I thought that since the clauses in level 2 was B1, B2, B3, and B4, right? So I was just saying that sorry, B3 and B6. So I'm saying only the B6 will drop out of CC1 at level 1, right? Sorry, level 2. So after backtracking, you'll yeah.
Yeah, so these are actually level 1 clauses. Okay. So
Yeah. Those are level 1 classes, but you're at level 2, so even those will be like propagated before you move on to make further decisions. So then,
exactly.
yeah, so then CC1 will just kick out B6 at that point, right?
Yeah. Yeah, so I think the problem here is that like because CC1 is not becoming a unit literal is because we don't have a unique identification point here. Okay. So what usually happens is that when we get a unique identification point and when we cut.
See, there are two ways to view it. I think the confusion here has been, Devjit. So this one, see, theory, there is something called theory propagation as opposed to theory conflict. You have to distinguish these, these two things. So here, as a result of all the decisions that you made at 3, 1, 2, 3, 4, 5, and 6, you could say that, this wrong decision as a result of B. So there is a conflict here. Okay. Yeah. But so why is it not, I'm a little puzzled as to why it is not getting reduced to, what is the UIP here?
Yeah.
I mean, maybe you should not be backtracking to, level 2. So because this one has some level 3, and level 5 clauses as well. Okay.
Yeah.
So if you backtrack to a later level, so this conflict occurred at level 6, correct?
Yeah. Yes.
So in order to, so you should be actually, why did you backtrack to level 2?
I mean, because if you look at the cut here, right?
Yeah,
if you look
but
at,
if you put the cut there, you will also have, so the cut should be something like this. So you will also have B5, whatever decisions that were made at 5. So in the clause, you look at the decision, okay, level other than the current one, okay, which is the UIP, okay. So if you want a unique thing, so B45 is unique, okay. So I would say that you have to backtrack to level 5, okay. In which case, all the other decisions will be retained, okay. And then, I'm sorry, you will be backtracking to level 5. So all the other decisions, 1, 2, 3, and 4 will be retained, and 5 also. So put back CC1, okay? Put back CC1.
Okay.
Yeah, so, and then it will flip. Then in that case, it will flip whatever the decision that was made at level 6 automatically, okay? It won't even allow you to make that wrong decision on B8. That's what will happen,
No,
Okay?
no, so no, again, but the thing is that a B8 have to be true. So it will again, okay, so maybe I skipped a step. Okay, I get it now. So basically this is the conflicting clause, right? Anyway, right.
Yeah, that you
Now,
got because as a result of making decision B4, B6, and B7,
yeah,
the
but
theory inferred that it should be not of B8, okay?
yes,
And then, but you had already made a decision of B8 to be true, correct?
but it has to be true.
Yeah, but that you had made at 6.
No, this is B8 is literally just a clause, so it has to be true.
I do understand. But I mean, when you say it has to be true, you will have to make a decision on B8.
Okay. I
So
get it.
is B8 a decision that you made here? No, not yet.
No. Oh, okay.
So, which means that you automatically derived that, as a result of making the decisions, B8 had to be false, correct?
Yes. Yeah.
So
Okay.
then the conflict resulted in this decision that was derived by the theory solver, and by plugging into C8, you got a conflict. That's how it would be. Yeah.
Yeah. Okay. Yeah. And
So
that's
it would not
similar.
be like what you pointed out here. So C8 would be resulting in your conflict.
In a conflict. Yeah. And similarly, C7 also would result in a conflict. Right. Yeah. And then B6 also again would result in a conflict, just like you said it would happen. Right. Okay, I have like skipped that.
Yeah.
But it will eventually come here. So I guess now we are back on track. It will eventually come here, right?
Correct. So there are several levels at which it will go, and finally, what happens?
Finally, we will. So finally, this becomes a unit clause, right? Because B8 has to be true, B7 has to be true, and B6 is implied to be true, and because we backtrack it to level 2, so this becomes a unit clause eventually. Okay. Now, as this became a unit clause, this decision is flipped.
Yeah.
So this becomes this. Okay. Now we take more decisions. That is B5.
This decision on B4, because your indices are so invisible that makes it difficult.
Okay.
So B4 is it? Okay.
Yeah.
That is B4. Okay.
Yeah.
Yeah. So B4 gets flipped, correct?
Yes. Right. B4 gets flipped. And then again, we make a decision on B5 to be true, B7 and B8 similarly, just like how we did right now. Okay. And then we see that there is another conflict. I'll show you the conflict. The conflict here is not of B3, not of B5, not of B7, not of B8. Okay. Now let's see how the conflicts are. So here we say that V21 equal to V11, and again B5 says that V22 equal to minus V11, which will make V311 to be 0. So that's how we get another conflict here, that V31 to be 0. Okay. So this is again another conflict. Now, once we have both of these conflicts, you will see that it's, so if we backtrack it to level 2 again, okay, we will choose not of B4 again here. Okay. Now, because so we will also have to choose not of B5 here. Okay, because B7, B8 is true, but again what you said is that like it will again happen that like B8 might be true. Again, I will get a conflicting clause that like B7, B6, B7 and B8 have to be true. Okay, just like in the previous case which you explained right now, that like B7 have to be true, B8 have to be true, and we'll backtrack it again. So that is what I seem to have missed here again. Okay. So B3 is true. It means that these will be a unit literal again, and B5 have to be false. Okay. So B4 is false and B5 is again false. Using these two conflict clauses, we get this. Now again, B7 have to be true because it's like a conflict, because it's literally a clause, and B8 have to be true. Okay, let me zoom in a little bit. And again, we say that B9 is also true. Okay, and if we send this thing into a T solver, we will get a solution. So this is how the DPLLT algorithm usually.
So the B9 decision was an explicit decision that you made, correct?
Yeah, it's an explicit. Yeah. So this is how DPLLT.
So is a conflict clause missing from your analysis or no? Should there?
Yes, because you said that so it would backtrack to B2, like in this case. So there will be some more. Yeah, there will be some more conflict clauses here, and it will only contain like not of. It will only contain B7, B8 again. Yeah. So this is how the DPLLT algorithm works. Now I'll explain how
so in a summary, so you had to generate 3 conflict clauses and you had to backtrack 3 times here, correct?
Yes.
Yeah, I mean, just for comparison, I'm saying, so just when you later look at Reluplex.
But not only that, but like we will also have a lot of simplex, like T solver queries, right? So in that case also, I'll show that Reluplex were way better.
I mean, so they were at each point, so there's actually only 3. I mean, every time that you checked, the checking of whether there's a conflict or not was a result of T. So here, fortunately, the one thing is that there are some things which you could have got. Okay, so you're always generating a conflict clause by sending the current partial decisions into a T solver.
Yes, right? Yes.
Yeah.
Now the T solver.
But after you made the a decision. So no. Before you go, let's keep it clear. So there is something called T propagation. So see, either you could also have, which is what is a little bit being unfair to this T solver. You could, as a result of B4, B6, and B7, which are explicit decisions that are made, correct? Before you did this, before you generated CC1, you made a decision on B4, B6, and B7. Am I right?
Oh yeah, I get what you're trying to say. Yes. Yeah.
Then, if you propagated that, no. You would still have to. No, I'm sorry. No, I take it back. Okay, because as a result of that, you would already have. No. I would say, I don't know when you made the decision. All of them are conflicts. Okay, you're right. In this case, there's nothing. So, see, sometimes the point I'm trying to make is sometimes your theory propagation itself will give you a decision. Okay, which is. Which you could make, which did not happen in this case, okay?
Yes.
Because you made the wrong decision. Therefore, both the decisions on B7 and B8, which were obtained, so you could have, So, I mean, the order in which you made the decision was such that there was nothing that you could infer from theory propagation
Exactly.
To guide your wrong decision, okay, to
Exactly.
prevent you from making the wrong decision, okay.
Yeah.
But that if indeed you had decided, say, on B7, B8 or something like
Exactly.
that,
Exactly.
okay, then you would have, it would probably have prevented you from making the wrong decision on B8. Okay?
Yes. 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 Yes.
So
that
is
is
the point I'm trying to make. Okay.
Yeah. So that is why I chose this order. So
Okay,
that I
make
could
it,
show you like all the things. Otherwise,
yeah.
in like there would be no conflicts at all. We could have just done it like that.
Yeah, so there is a possibility where if you chose to just, instead of 4 and 6 or something like that, if you made a decision on B7 and B8, okay, first,
Yeah.
you could have
Yes.
probably had a better convergence.
Yes. Definitely. Yeah.
Mm.
Yeah. So I mean, it depends on the order of things which you give.
Mm. Mm.
Yeah. So that is it. So I'll continue the next part. So here, so our problem was to basically verify properties for DNN, which will have ReLU activation functions. So here we used quite a general framework for solving this problem, which is DPLLT. So we will try to use the properties of ReLU and how things are to get a better
Before you do that, I want to raise another question. Okay.
Yes.
So, is it? See here, you made a decision. Okay, could the fact that yeah, I mean, maybe I'll ask this question after you choose show Reluplex. Okay, in Reluplex, there was a very efficient proof that in the way that Madhukar illustrated, without actually based on a decision, you could, even without using ReLU, abstracting ReLU away, you were able to get a solution. Remember? Okay. So he was assuming that there was no ReLU and so on. But okay, so let me pose this question. We can get back. Okay. So does it, instead of making decisions on these equalities and so on, okay, if you biased your decisions as Boolean variables on the on these antecedents in the implication, okay, will it help? Okay, can that be a heuristic? Okay, so instead of would it help to make a since you have a choice in the order in which you make first the decisions on these antecedent variables, okay, or the other way around. I don't know. I mean, which would be better? I mean, I think in order to get that some intuition into that heuristic, what would be a good exercise to do would be to take the Reluplex, the most efficient proof in Reluplex, okay?
Okay.
And then see if there is a sequence of decision order that you can get the same kind of efficient proof here. Okay.
Okay. So I mean, like sometimes even in like DPLLT or even in Reluplex, people use this ordering that like if B1 occurs the most number of times in the literals, they take that to be the first thing to be decided.
Something like that heuristic.
Yeah.
So in order to get what might work, what might be interesting, what I'm saying is take the an efficient proof of Reluplex, okay, and then see if that can be recreated here by by making certain decisions that are favorable to you. Okay, so will that proof give you an idea for the order in which you have to make the proof? Okay, so I'm making a claim, okay, that if you do that, and which is true or not, I don't know. After you describe Reluplex proof, can you simulate for the shortest proof in the Reluplex? Is there in decision ordering, which will comparable proof here as well? Okay, I'm saying that there probably is. Okay, if you pick the right kind of decisions that matter. In the case of Reluplex. Okay, so that is a question that would be interesting to investigate. The same kind of efficient proof that you got in Reluplex, can it be simulated here by a suitable ordering on the decisions to make? Okay, so do you get
most cases? In most
cases, I mean, it may be possible, is what I'm saying. But how do you determine that is a different thing? This is still a kind of a theoretical question. Okay.
I mean, proving it would be like pretty hard, I guess. Like,
I'm not asking for a proof. I'm just saying, okay, maybe it suggests a way to make a decision on the thing. I don't know.
Yeah. Oh, that is interesting. Like maybe.
I mean, since you are there as a human being, one way to do is to, can I simulate? Can I pick an ordering such that the the proof will be just as efficient in terms of the number of decisions and number of calls that you're making to LP? Okay, so that is what I want to investigate.
So Reluplex is simulated by the simplex. Or
yes.
The
yes. Or the DPLL. Correct.
Yeah.
Is there a way to simulate it? Exactly right.
Yeah.
That's what.
Yeah.
And I feel that there is a way. Okay. And that is picking the right decision. Okay. And then Reluplex proof can give you a hint as to what that thing is.
Yeah. No, but then there is okay. No. So I don't think it's possible, because there was this thing which was written in the paper that, like, at worst case, I mean, like at a lot of cases, DPLLT would actually split the ReLU 2 to the power n times itself.
But no.
But the decision. Okay. But the decision.
I'm saying now that you know that there is a proof.
Okay.
That gives you hints. So,
Yeah.
That should happen.
Yeah, that makes sense.
I mean, a priori, you may not be able to guess that. Okay. But once you know, you have a Reluplex proof, then there should be a way to simulate it, the same kind of decisions and splits and so on.
Yeah. Okay. That definitely will be possible.
I mean, that still would be interesting, okay, for you as an exercise to do. Because after all, see, Reluplex, I know that I'm getting ahead of the thing. In Reluplex also, if you use a fully eager thing,
that will again give me.
That will be very exponential. I mean, if you compare the eager Reluplex with respect to some smart decision heuristics, DPLT might come out ahead. Okay.
Yeah, indeed. Yeah.
Okay. Please. Sorry for the interruptions. Okay.
Okay. So I'll get to the next part, which is trying to use Reluplex. So here the problem was that we had like a lot of ors here. That is, like, we had this implies this, something like that. So at worst case scenario, we would have to go through all of these propositions, which will result in 2 to the power n propositions. So here is where Reluplex comes in, and it sometimes does not split the ReLU activation node into two parts. It will only split when it's needed. Okay, and I'll illustrate it using this example. Okay, now
but before you do that, can you refresh our memory? See, I certainly want, because I have some doubts that maybe Madhukar can also clarify. So can you go through the inference rules, specifically the update inference rules? I mean, I don't know if in your presentation you were planning.
Yes, I have them.
You will. Okay. Then I will wait till that time. So because I have some questions about and doubts about the update inference rules that I want to raise. Okay. And I will raise it at the time that you will present that. Yeah. Okay. Go ahead.
Yeah. Okay. So first of all, here we actually split the ReLU function into two parts. So we consider this as a whole ReLU node. Okay. But we split it into two variables. That is VB21, which is V21 backward, and V21 forward. Okay. And like similarly, we do this with this. You will see that how writing equations using these variables will help us a lot. So first of all, we write this equation, which is essentially will help us to push the equation into a ReLuplex solver. And that is essentially saying that, so any ReLuplex solver will have a lot of equations, and all variables have a upper bound and a lower bound. Okay. And we have ReLu pairs, like here VB22 and VF22 are ReLu pairs. And again, VB21 and VF21, this is another ReLu pair. So ReLu pair, we have to check. So we always have to make sure that the ReLu pair remains are satisfied. Okay, eventually they are all satisfied. Okay, so that is something which we look into. And again, we always have to make these equations satisfy. But the variables can get out of bounds, but we would always like to have these things satisfied. Okay, now I'll get into a bit of details. Like, so just like we saw how
just one small point that I want to make, it's a kind of follow-up to that simulation of whether you can simulate this proof. I think what would be useful is go up.
Okay. Here.
Now, you could have used exactly this encoding as the formulas that you start out with in your DPLLT proof. Okay.
Okay.
With after you can introduce these variables, forward and backward variables. Have these equations. Okay. Then you can really make a one-to-one comparison. Okay. In order to simulate it is what I'm saying. Okay.
Yeah.
Then you may even because after all, DPLLT does abstract.
Hello. I don't think I can hear you.
Yeah, sir, your voice cut.
Yeah, I think sir has dropped for a while.
Okay.
The internet connection is probably.
Yeah. Okay.
Just wait for some time. What do you think, Madhukar? Should I call sir?
Yeah, no, he'll join back. Wait minute. Yeah, so let's wait. But I think the point that he was trying to make is that if you use this, so earlier, when you had encoded it as a DPLLT problem, you did not do the backward forward split, right?
Yeah, I did not.
Now suppose you had done a backward forward split, and now suppose this is what you write as the constraints. Now, of course, you'll write a number of constraints, and somewhere you will also write the constraint that VB 21 less than 0 implies V21 F.
Exactly.
Okay, so these are some constraints that you will write. So consider these 4 constraints as the last set of constraints that you write.
Yeah, then it will converge faster.
Yeah, and I think somewhere he was saying that if ReLuplex can converge faster, it means that those 4 decision variables are, they can be decided on later. You don't really, if Reluplex can converge without really worrying about the relation between forward backward things, it means that
Yeah.
the corresponding variables can be decided much later. I think this is the point that he was trying to make.
Yes.
But he's here now, so we should be
Yeah,
able
yeah,
to.
I'm here. I'm here.
Yeah.
Sorry, some internet issue.
Yeah. No issues.
Yeah, can you repeat what you were saying, Madhukar? Yeah.
Yeah. No, I was just saying that, if you take the same figure, the figure 7 as we are seeing right now, and encoded this as a DPLLT problem, then along with a lot of other constraints that you have, you will also have the constraint that if backward is 0, if backward is negative,
Correct.
it implies that the forward is 0. So,
Yeah,
so there are 4 such constraints. Backward
Correct.
negative implies forward 0, backward positive implies forward backward same, and similarly for VB22.
Correct.
So there are 4 such constraints. Now, if you write those 4 constraints towards the bottom of your constraint list and have 4 Boolean variables which represent these constraints, then these 4 Boolean variables should be decided at the fag end of your decision-making process.
Yeah.
Because if
that's right.
Reluplex can solve it without really worrying about these variables, then DPLLT should also be able to
That's
solve
right.
it.
I think
That
that is what I was getting at. Yes. So yes. So if you encode it in terms of these variables, it'll help you to abstract that thing away. That abstraction that is already happening in Reluplex. You could simulate in DPLT. Yes. Okay. Good.
Yeah.
That's a better way of explaining what I was trying to put forth. Yeah. Yes.
Yeah.
And that will also suggest kind of a decision heuristic, no? If you want to delay that.
Yeah, exactly. You're basically delaying the split in some sense.
Good. Yeah.
Again, even there. Yeah. That is exactly what Reluplex is doing. Okay. So again, so in Reluplex, what we would like to have are these equations, and every equation, every variable will have a upper and lower bound. Now the equations cannot be so the equations must hold at all times.
Can you take it to full screen? Why are you?
Oh yeah.
Reason why?
I don't know what is happening. Just a sec. Let me check.
So it's not in full screen mode.
Yeah, I don't know what is happening. Just a sec. I think this will work. Just a sec. Let me open it again. Yeah, I think this is fine. Right? Oh no.
Yeah.
Oh, okay. This is working. Okay. Left, right is working. Okay. So now, wait. Yeah. So now, what we have is that we have this these equations which were here. I don't know what is happening.
No, I think there are 2 ways to go to a full screen. Either you could say full screen mode, or you could say, I mean, you're using this slide show mode or something like that. That's when this thing comes up. Instead, if you go to full screen mode, either go to view and then say not slideshow, but you should. Oh, but you are using that only. Okay.
Yeah, even I guess this is fine. Okay, so yeah, so suppose we have these equations here, and we would always like these equations to hold at all times. Okay. What is so now every variable has an upper and lower bound. So we would like these upper and lower bounds of these variables to hold at all times. And we have these ReLU pairs, which can not hold at times, but we would eventually want them to hold. Okay, and we would make them hold using these update rules, which I'll explain right now. So here in simplex, we had pivot 1. That is, if a variable was less than its lower bound, we would increase it eventually. And again, here we had pivot 2, is that if we had a variable which is greater than its upper bound, we would lower it. And if we and then we had this update operation, which would update the value a little bit, so which would update this value, which is not inside the basic variables. Now, what are basic variables? These are basic variables, as in A1, A2, and A3 are basic variables. Now, basic variables cannot be updated. Okay, so if you want to update a basic variable, you have to first pivot it with some other variable, and then you have to update it. Okay, now we also have a failure thing, that is, which says that you cannot update anything and it is still unsat. That is when failure happens. And again, success is when everything holds, every upper and lower bound holds. So these are the things which were in simplex. Now we will have these rules, but we will also have rules such as update B and update F, as in like if the ReLU pairs are not satisfied, we will increase the values of V21F and V21B, so now again, to update the values of these ReLU pairs, any of these have to be in a these have to be non-basic variables, because again, only non-basic variables can be updated. So these are here. Okay, so now this is a thing which says that if, let's suppose, the backward edge, that is like V21B is to be updated because it's like not inside the ReLU pair, we can either update V21B or we can either update V21F. So update B essentially updates the V21B, and update F here updates V21F. Now again, pivot for ReLU.
Wait a minute. This is where I have a question. Okay.
Yeah.
Now, I guess update B and update F update B updates the input Xi, whereas update F updates the output Xj.
Exactly.
Correct?
Exactly.
Do they update so that the ReLU pair, ReLU constraint will get satisfied?
Yes, exactly. So that
that is where I had a doubt. Let's suppose, okay, maybe I'm making a mistake in my calculation. Let's look at update B.
Okay.
Now, let's suppose that Xi, Xj, Xi is say 3 and Xj is 4. Okay. Obviously, if Xj is 4, Xi has to be 4 as well. Correct.
Yeah.
Now suppose it is 3.
Yeah.
Now here he's updating Xi to the difference between those two things. Okay.
Yeah. Which is 1.
This will be 4 minus 3.
Yeah, which is 1. Yeah.
Which is 1. So how will that satisfy the ReLU pair after the update?
No, update here means that we'll add some of this variable here.
Is that
so
right?
just like here. Yeah. Exactly. So update means that we'll add the variable.
I see. Okay. I mean, that's why I interpret. So so the theta, it will be updated by whatever the existing value is, and you will add that.
Yes.
Yeah. Okay.
Yeah.
Okay. Got it. Yeah.
Okay. Yeah. So now we also have this rule called ReLU split. Okay. Because suppose we update it and we pivot it. Okay. We can again go into this update B cycle and again come to pivot ReLU cycle. So it can cycle a lot. Okay. That is like, suppose we update this. Okay. And then we pivot A1 and then we update this again and then we pivot A1 again. So I'll show a case where this cycle keeps on happening. And if it happens for a long time, we do a ReLU split. And I'll explain what ReLU split entails using something called decision trees. So let's take an example. So let's take this example. I'll actually share my slide here. Just a sec. What is happening? Okay. No. Just a sec. Array. Yeah. So now, as you could have seen, what I'm doing is that I'm essentially taking all these
So
things.
you made a comment that there can be a lot of cycles, and I mean, in motivating the need for pivot for ReLU
ReLU split.
or ReLU split. I mean, ReLU
Yeah.
split, correct. But actually, ReLU split, without ReLU split, you will get you could get stuck, no? So you not like it is not being used to avoid cycles, but rather,
yeah, it is not.
Yeah, you will end up in a deadlock. No, so that's why.
Yeah.
At that point you would have to ReLU split. Okay.
Yes.
Not to avoid cycles.
Not exactly to avoid cycles. Basically, if it's going on for a very long time, you would rather split. Right. If V21B and V21F is kept on changing a lot of times, you would rather split. So it's in some sense, what is it called? It's a trade-off.
Is so there are two things. Okay, so maybe Madhuka, you can chime in too. So the doubt I have is, so if both of them are, you see this, if both of them happen to be basic, then you get stuck. Nah.
No, so he's talking about ReLU split, not the pivot for ReLU.
No. What I'm saying is, if your ReLU pair constraint, if ReLU pair is broken, and if both of them happen to be basic variables, the xi and xj, then you are stuck, correct?
Then you need to use the pivot for ReLU.
Oh, then you have to use the pivot for ReLU.
Yeah.
Yeah, ReLU split is when the same ReLU pair keeps breaking again and again.
Okay. So the stuck is used for pivot for ReLU.
Yeah.
So that's why, yeah. Okay. ReLU split you will use when no matter how much you try and do this, okay, and so you're never able to satisfy, right? The ReLU constraint. Then you will put a bound up in the, okay. Go ahead. Yeah.
Yeah. So now I'll just take this table into a better Excel sheet. So here we had.
So what is this table? You're using to illustrate every row here is one step, application of inference rule.
Yes, exactly. So this is the first assignment. Okay, which is all of them are 0. Okay, now these are the variables. Okay, and these are the equations which were there in the tabular. Okay, so now we had these equations. Now, if you notice, the first thing here which will apply is the update rule. Okay, the update rule from the simplex, which is also there in Reluplex, which is V31. Okay, this is out of bounds. So we increase this. While we increase V31, it will also increase the value of A3. Okay, so A3 also increases to 0.5. Okay, now as A3 is again out of bound, but again this is a basic variable, right? This is a basic variable here, right? Because A1, A2 and A3 are all basic variables. This is a basic variable. So to actually change it, we will pivot A3 and then we will update it. Okay, so in the next thing we pivoted A3 with V21F. Okay, and we updated it to 0. So this is what we get now. Just a sec. Yeah, so now what will happen is that there is a ReLU pair breaking here. Right.
Debjit, so you have update. Update B and F are special kind of updates, but there's also another update, I guess.
Yeah, there is another update. Yeah, which comes from
regular update.
from
Everywhere
simplex.
Yeah. Okay. Okay. So that's what is being different. Okay.
Yes. Yeah. So now what will happen is that you'll see that this is a ReLU pair. Okay. And it is breaking here. So we will update v21b, and this can be done because this is not this is a non-basic variable. Now once we update v21b, it will also increase a1 to 0.5. Okay, so now this is out of bounds, so which we pivot it again with v11, and we update it and we change it back to 0. Okay, now once we have changed this back to 0, v11 changes to 0.5, which in turn changes a22 so which in turn will change, and it also updates a22 to 0.5, because v21b which was here is 0.5. Okay, so v21b is 0.5, a1 is 0, and this is 0, so we get this a2 to be out of bounds again. Okay, now we pivot a2. Okay, now this is out of bounds, right? And this is a basic variable, so we have to pivot it again using v22b. Okay, once we pivot it to v22b, we'll see that like we can change a2 to 0, and v22b changes to 0.5. Okay, because a2 is 0 and v21b is 0.5, so v2b changes to 0.5, and this gives us ReLU success. Okay, now so this gives us ReLU success, and so it's a satisfiable condition. So if you look I'll explain this later on. Okay, so this gives us ReLU success. Okay, now let's say we had assignment 3 here. Okay, now the difference in this thing and this,
so these are two different proofs.
no, exactly, so we pivoted here using a different thing, and here we'll pivot it using a different thing.
Okay.
Okay, so here we pivoted it using v11 with a1. Okay, here we'll pivot a1 with v21b.
So what does star, double star mean here? So
so these are just variables, nothing else.
No. You have put asterisks to me.
Yeah.
As a legend, I'm asking you. I'm asking you what does star mean? It is different than assignment 3, using a different pivot. That's
yeah.
Okay.
Again, the thing is that this will cycle again, so that is why I put asterisks here. Okay, so once we have v21b, okay. So here again, what we did is that so a ReLU pair was breaking, so we did this. Now again we see that a1 is out of bounds, so we pivoted using v21b here, whereas here we pivoted with v11. So that is why it worked. Okay, but here it won't. Okay, here it won't work because we'll pivot it.
So what the operations you're using in each of these steps here are update, pivot, update, pivot, update.
Exactly.
Okay.
Update, pivot. So here again, we did an update pivot, but we pivoted it using v21b. Okay, so we get this. Okay, again we see that a ReLU pair is breaking, so we again set it here, and we get back this equation.
Yeah, so actually using update B and update F here continuously, isn't it?
No, so here we are using update B. Okay, this is update pivot.
Correct.
Okay, and
so
this is update.
It would be nice if you had those inference rules also listed. Yeah, on the right side. For some reason,
here I guess.
Yeah, you decided to omit them. Okay.
Okay. So, but I have this slide, so
No, that's okay. No.
it will
Make your point.
explain
Make your
things
point
here.
there. Yeah, make it
Haha.
there.
Yeah. So here you can see that we are back again to the same assignment, which was in assignment 3. So if we do the exact same thing again, it will cycle, right? So we will be stuck in a cycle here forever if we did not do, which is called ReLU split.
Now, one thing that you're not doing here is, that's good that you're illustrating that you need something more. Okay, now, but could you have prevented, go back to the thing, because here you're not, it seems like you're not using any variable ordering, or are you?
No.
Yeah, but could you have prevented this this thing if you had used a variable ordering? Probably not. Okay, so that is the important question. Okay, so because in Reluplex, in simplex, also there can be loops. Okay, and you're not careful. Breaking that loop and ensuring that it does not cycle forever is through variable ordering. Okay.
Yeah.
So, but here there is these cycles cannot be prevented even if you used a strict variable ordering, which you will have to use here anyway. Okay.
Yeah.
In order to ensure that the simplex operations, the regular simplex operations don't run into cycle. But what you're pointing out, I presume, here is that even if you used a variable ordering, you couldn't have prevented this thing. Okay, because it is coming due to a ReLU pair thing. Is it? Am I right?
ReLU pair, So exactly. So the ReLU pair breaking is what makes the cycle into an infinite loop. Yeah. So that is what is happening here, and that is why we need ReLU split. Okay. So now this ReLU split is can be seen very nicely once we use this derivation tree thing. Okay. So here a derivation tree is basically a bunch of tuples like this. That is B naught, which is the basic variables, and T is the tabula, which is the tabula of equations. The L naught is the lower bounds of the variables, and U naught is the upper bound of the variables. This should be alpha naught, which is the assignment of the variables.
Okay. So just a point of administrative things. So we are at 11:53. I know that today is Thursday. I don't know what kind of constraints you have. It'll probably take you another 10-15 minutes for you to.
Yes.
Okay, so now I'm going to ask if everybody is willing to be there till 12:15. Yeah.
Yeah, I'm fine. I had a class, but it got cancelled, so now it's okay.
Okay, so then let's relax. Okay.
Yeah.
Let you finish. Okay. And then I have. Yeah. Go ahead. Yes, you're explaining derivation and derivation trees. Yes.
Yeah. So derivation tree is basically taking everything into a node. That is, taking whatever we have in a row like this, that the assignment, the lower bound, the upper bound, the equations, the basic variables, the ReLU pairs, everything into a node. Okay.
So can you once again explain here? So B naught is the basic set of basic variables.
The set of basic variables.
C naught is the tableau.
The L naught is the lower bound. The U naught is the upper bound. The alpha naught is the.
Well, alpha is missing here. So
alpha is missing here. Yeah.
Alpha naught is
the assignment.
Okay. Alpha is the assignment. Okay.
And R naught is ReLU pairs. So here.
ReLU pair. Okay.
Yeah. So here I have the assignment 1. So assignment 1, we update it. We get assignment 2. That is, we updated V31, if you remember. We get A2, and we use pivot. We get A3. And so this should be pivot plus update. Okay. So pivot plus update gives me A3. And then again, we update B. So the thing to notice here is that we did not use ReLU split at all. And that is why this tree is in some sense linear. Okay. So tree in here is linear. Now here I have just showed the tree for the cycle. So this thing goes very long eventually, right? Because it will come again and again. Okay. So to break that, what we do here is that we do a split. Okay. We do a split. So we split the problem into two parts. That is, one will have that v21b is less than 0 and v21b is equal to 0. So this is one condition which will be in the sub problem here. And the another sub problem will be saying that v21b is greater than 0 and v21f is equal to v21b. So these are two parts of the problem. So this is exactly how in some sense DPLLT splits. Okay, but here we are splitting only when we need to split. So there is a trade-off there.
Yeah, but there's also another thing as part of your strategy that you will have to use. I think that you cannot kind of willy-nilly mix update Bs and the usual simplex rules. Okay, so here I think the strategy, implicitly what they are doing is you will have to first do all the simplex operation, and then there is your strategy is doing first doing the simplex thing so you can get all the constraints, and then there is an order in which you will have to first do all the usual pivot and update using the classical simplex rules.
Yes.
After which you do the updates. Okay,
I agree.
Update B and update F.
I agree.
Then you come back. Okay. So that is also important, because you cannot willy-nilly do one small update B, then come back here, and do a little bit of classical simplex, and then you cannot mix that. No.
So what I mean here in this place is that we pivot it once. Okay. And if we had needed to do an update, we would do an update, but there was no need. And that is why we used update B.
That part I understood.
Yeah.
But what I'm saying is that there is, and I think in the appendix, even without splitting, there is an additional, point worthy of note in the strategy. Okay, if you could go back to go to that appendix. Okay, so there, in the paper, he uses a strategy. Okay,
here.
You see. This strategy is important. Okay. Look, I mean, read it out. Okay.
Okay. Oh yeah. So, our strategy for applying Reluplex rules was to repeatedly fix any out of bound violations first using the original simplex rules, and only afterwards to correct any violated Relu constraints.
So this is also important. Besides doing the Relu split that you're doing. Okay.
Yeah.
That is also important, is all I'm pointing out. Yeah,
indeed.
That's what you illustrated here. I don't know. I mean, but so there are several things. Okay, when you're using the classical simplex, you have to use a variable ordering. Okay.
Yes.
Otherwise, the classical simplex part of the strategy itself may go forever. Okay. But to that, you will have to finish up with the classical simplex for updating, and then you come to updating the Reluplex. I mean, the fixing the Relu constraints. Then you have, in addition to that, if you keep on, if that update, fixing the Relu pair part itself appears to going forever. Okay.
Yeah.
That's the way the cycle that you mentioned. Then you do Relu split. Okay.
Yeah.
Am I right?
Yes.
Okay.
I mean, like even here, I think I have done that because I have pivoted and updated, and then I saw that like something is missing.
Yeah.
That's why I updated it, and then again I pivoted it. So yeah, I should have added an arrow here, I guess. So I pivoted it once, and then I saw something is So one of the ReLU pairs needed update. So that's when I updated it.
Mm.
So again, this thing goes on. But yeah, I get your point. Yeah. So once we split this problem into two, we can again use the reluplex thing over these two sub problems.
Mm.
And if needed, we will split more. Okay. Now another thing to show is that what happens using eager ReLU split. Okay. So using eager ReLU split, we will split the first V21 into two parts here, right? And for each of these, we would split it into two parts again. So we will get 4 sub problems in total. And over each of those, we would rather use simplex. So here in this case, if we use eager ReLU split, it will be way slower than DPLLT. Just like Sir pointed out few moments earlier, that like if we use eager ReLU split, it will perform way worse than DPLLT.
Yeah, on an average, because
On an average,
it's exponential all the time here.
Yeah, exactly. It is exponential all the time.
Mm-hmm.
But other than that, it won't happen. Yeah. So I guess yeah. So this is all I had up till this point.
Yeah, I think what would be interesting for you to do is, kind of try and simulate, okay, the same thing. You take a derivation tree that gave you a lazy split, okay? What you showed before is a lazy split, okay, where you did only when it was needed. Some cases you may try to get a proof. Okay, have an example of a proof of reluplex in which you did not need a split at all. Okay, try to simulate that in DPLLT.
Okay, yeah, I get it.
And have a very compact proof, reluplex, where you needed maybe one lazy split. Okay, simulate it in have a DPLLT. So pretty much you could implement the reluplex strategy inside as a program over Z3. Okay.
Yeah.
So, but I'm not asking you to do that. I'm saying just do two exercise. One is where you will simulate the reluplex proof in a Z3. Okay, and then I want you to show it to. I mean, just I'm not going to ask you to represent it or anything. Maybe you can just submit that, circulate it among the results to have us give us some confidence that you can actually simulate them. So two things I want you to do. One is take an example where you did not need any split at all in reluplex. Okay, simulate that in DPLLT.
Okay.
Take another example of where you needed maybe one or two lazy split. You had to do because you went into that loop. Okay.
Yeah.
Then, and after doing a ReLU split, you were able to get the proof. Simulate that also. Okay.
Okay.
And by simulating, I mean you have to pick the right kind of decision ordering on your variable, so you'll get the same proof. And I want to see that.
Okay. So I'll actually do it by hand, I guess.
Yeah.
Right.
You will do it by hand, but you will document it. Okay.
Yeah.
Document. Okay. So you will have your derivation tree here for reluplex proof, and you will have a DPLL tree decision tree, so that you can side by side compare.
Yes. Indeed.
That I want you to submit as a follow-up.
Yeah, sure.
Follow up, circulate, and so we will know. So that's all the questions that I have. I mean, any other questions that other people have? Any questions, Madhukar?
No, I guess I was just thinking about what you were saying regarding the idea of comparing like these two things. I think one of the things why this reluplex becomes very fast is because of these, like they probably would have like long stretches where they're just sitting inside simplex, and Yeah, and those would probably be very fast in just the simplex or the linear conjunction domain. So in some
Even
sense,
even without. Yeah. So whereas here you have to go back and forth, right? In DPLLT. Huh?
yeah.
Mm.
So I think so in that sense, because we're maintaining one concrete variable assignment in this thing, and we're doing these long stretches of simplex, this allows us to in some sense figure out which are the constraints that we need to fix first in some sense, right? Because after you do a long stretch of simplex, only some of the ReLU constraints will be violated, and only those you'll need to fix. Whereas the similar thing may not be there in DPLT, right? You'd have to guess over that in DPLT.
It's possible. See, man, the purpose of my doing it is I can really believe what you're saying, that it is not to I'm not claiming that I can get the same efficiency at all, okay? Because it's so tightly integrated within simplex. There are a lot of engineering advantage in addition to maybe like what you mentioned you get here, okay?
Right, yeah.
But to kind of conceptually understand, okay, what is going on, huh? So I thought it was interesting to see.
That'll be interesting as I think so as well. But
but I agree with you. I think.
But I think I mean, what would be interesting is to see is how the variable ordering that would work out in DPLT emerges from the ReLU, like the simplex calculations here, right? Because that's the only place where it can come from.
Yeah.
Because all this is doing to.
No, I mean like there is the order of the clauses in DPLT also matters, right? Not only the order of the simplex calculations.
But I mean, so if you're going to translate a ReLuplex proof into a DPLT proof, you're translating something into an order of the variables and order of the classes, right?
Yeah.
So whatever that you have that you're translating here is coming from, I think, all the simplex crunching that it's doing in these stretches. Because basically what you'll be translating would be in some sense encode which are the ReLU constraints that you want to do some theory propagation on, right? And in DPLT, right? Because
I think both of you are making the right point. I think this point that Debjit makes, that the order of the clauses are also important, is because there is one layer of abstraction that is going on that is not there in ReLuplex, that is there in DPLT, which is this Boolean abstraction. Okay, so so because that is not there here. So because when you throw away that information, maybe you will be making some decisions, useless decisions,
blind decisions in some sense, regarding what clauses that, for example, if you have crunched some simplex, then you don't need to do some propagation or spend some time propagating things for a clause that is for a ReLU pair that is already satisfied. So if you fix some of the directions in which your simplex or the non-ReLU clauses are, then already you shouldn't have to do all of that.
Right. Any other questions, Amaya?
No, sir.
Madhukar, do you want to add anything?
Nothing.
One thing that I wanted as a, not on this presentation. Thank you, Debjit.
Okay. This is
quite detailed, and so the details will certainly help to understand the next class. Okay, so about the derivation tree, and so on the next presentation. So my comment was just a follow-up comment that I thought of on Amaya's presentation. Okay, so what Amaya presented was actually a sound only one part of the thing. Okay, so what he showed was, okay, if it terminated, that he showed that why it has to terminate if you have an ordering. When it terminates, if there's a satisfying instance, then if it says satisfies, If it terminates and then says satisfies, obviously the solution it produces is a sound satisfying solution. And that is guaranteed because of the invariants that are preserved. Okay. Now, the reverse proof to be complete, okay, the reverse, that if the original problem is has a satisfying instance, then the procedure, simplex procedure, is guaranteed to terminate, to say sat, okay, is not shown yet strictly. Okay, you did not show that. Okay, the reason the reason that is relevant because the simplex searches only through finitely many solutions. Even within that finitely many solutions, how do you know you know, that it'll, you know, with the ordering, that it may miss out on some solution? Okay.
So it's just equivalent to saying that if it gives, so if since you have shown it terminates, and if it terminates with sat, then it is actually satisfiable. I just need to show that if it terminates with unsat, then it's actually unsatisfiable. It's equivalent to what
you have
saying.
to do that, or you have to say that whenever there is a satisfying solution, there is always some solution that it that it will, in that ordering, okay, that it produces. Yeah. Because if you use the ordering, it is obviously, or you have to say that it'll get through, because it is not looking at even in that finitely many possible solution space. Where is the guarantee that it'll get to the satisfying, is guaranteed to get to the satisfying one?
No, because it doesn't terminate until then, right? So if it only terminates when the constraints are satisfied.
Yeah. So, but it may terminate with an unsat one, because because it may terminate with something which it may say unsat. But why should it, you know, but there may be a SAT solution somewhere else that it did not look through.
Yeah. So that, I can just do that in maybe in the beginning of Harsh's presentation. I'll just start with that.
Yeah. I mean, what I'm saying is, even if we don't find the time, because, you know, that will be unfair to take away time from him. Okay. So what I was saying was just like I gave you a follow-up assignment to Debjit. Okay. I want you to just list as bullet points why you know, how you an argument for guaranteeing that.
Okay, sure.
Yeah.
Yeah.
Then you know, let's see. So I will let in the next scheduled class, which we'll have to agree upon. We can maybe do by email, since Harsh is not here. You know, so maybe circulate it, and if necessary, I will at this time, we will let you present it as well. Yeah.
Okay, sure.